So good morning, everyone. It's so exciting to be here, meeting everyone in person and virtually. Today I'll be talking about recent Parquet improvements in Apache Spark. So first, a short intro about myself. I'm currently a software engineer working at Apple, focusing on Spark, mainly on Spark open source, but also touches other projects, including Hadoop, Parquet, Iceberg, and so on. Right now, I'm spending most of my time focusing on improving Spark SQL performance. I'm also committed to Spark, Hadoop, Hive, and Arrow. So this is the outline of today's talk. We'll mainly talk about two new features in the recent Spark releases. The first one being the complex type support for Apache Spark for the vectorized Parquet reader. And secondly, the column index support for Apache Spark. So before that, we'll also talk a little bit about Parquet itself, just a short introduction, enough information to understand those two new features. Because Parquet is a very big topic, we don't have enough time to cover it all. And at the end of the talk, we'll highlight some of the future work that we can do to further improve Parquet performance. I also need to talk about some of the motivation for this project. So as you may know, that Parquet is a very popular file format used almost everywhere in this data plus AI world, right? So vast amount of data is stored using Parquet. And on top of that, there are different compute engines, like Spark, that needs to query data from Parquet, right? And that's like the first step for any computation. So in a typical Spark query, data scan it usually takes a significant amount of time of the entire query. So if we can improve Parquet scan performance, they will potentially dramatically reduce query latency, improve query efficiency, and save a lot of money. I'm sure that many of you may already know what Parquet is. In short, it's a columnar format that was originally inspired by the Schema paper from Google, published in 2010. It has built-in support for complex types. That's mostly just a struct, list, and a map, those three types. It is a single format specification, but with different implementations, both in terms of projects and in terms of language. It's implemented in different projects, obviously, as you may already know, in Spark, in Trino or Presto, in Iceberg, in Impala, Hive, and so on, right? On a side note, this is kind of like unfortunate because ideally we should have a single implementation that's shared across different projects. But due to the historical reasons, people just implement their own Parquet implementation in different languages or in different projects with different maturity, different optimizations, but that's a different topic. So we will also have Parquet implementations in different languages, most popular one being Java, I think, but they also have implementations in C++, Go, Rust, Python, and so on. So here is an overview of a Parquet format. There are three key concepts in terms of how a Parquet file is organized. That is a row group, column chunk, and the page. As you can see on the right-hand side, we have a single Parquet file that is organized by a single row group. But in theory, a single Parquet file can have one or more row groups. Each of those row groups, again, can be organized by one or more column chunks. So the number of column chunks is equal to the number of columns in the file schema. By default, a row group has 128 megabyte by default. But in practice, many people may set it to be larger size. For instance, in HDFS, usually you set it to equal to the block size in HDFS, which sometimes is like 512 megabyte. A colon chunk, by its name, is a chunk of data for a particular type. It, again, contains one or more pages. Each colon chunk has its own statistics about the values stored in that colon chunk. For instance, the minimum value, the maximum value, number of nodes, number of total values, and so on and so forth. Lastly, page is the basic unit in Parquet for data compression and data encoding. Right? Parquet can employ different compression mechanisms to reduce the file size. Most popular ones being like gzip, LZ4, Snappy, Z-standard, and so on. Parquet can also use different encodings to encode the data depending on its shape. For instance, if your data has limited number of unique values, then Parquet can use dictionary encoding to dramatically shrink the data size. So a page has 1 MB by default. So this, comparing to a row group, this is much, much smaller. So here is how a data page looks like in Parquet. Essentially, there are 3 components inside a data page. That is the repetition levels, definition levels, and values. Right? For this talk, you don't need to really understand how those level information work, but you just need to know enough about what they are for. For repetition levels, it's mainly for representing the start of a new record. For instance, if you have a type that is a list of string, then this repetition level can tell you where is the start of a new inner list. So you can find the start of the list and be able to reconstruct that list. On the other hand, definition levels is to represent the knowness information of a value, to tell whether a value is null or not. Lastly, the value is used to store the actual value of the data. That is only for no values. For no values, is encoded using definition levels. So let's take a look. Let's take a simple example here. Suppose we have a page whose type is string. In this case, you can see the definition levels. We have 4 ones and 2 zeros. So for this particular schema, definition level equal to 1 means that the value is not null. While definition level equals to 0 means the value is null, right? So you can see this, for this particular page, it represents an array of 6 values. That is A, B, followed by 2 nodes, and C and D. And that is because for the third and the fourth definition level, because they are equal to 0, which means they represent no values. And this is not an example of complex type. For this particular case, the type is a list of string, right? Because it's complex type, so we need to consider repetition level as well. For this particular example, the schema, for the schema, it means the repetition level equal to 1 indicates the start of a new record, of a new list. So you can see that in the repetition level column, the first and the third value are 0, which means they represent the start of a new list. So for this particular example, it represents a list with 2 inner lists, right? The first inner list contains 3 elements, A, B, and a no. And the second inner list contains element no, C, and D. So with that, we'll jump into the complex type support for Apache Spark. So this is a new feature that was just released in Spark 3.3 this month. So some background information. So what is complex type? As mentioned earlier, complex type mainly contains 3 types. That is struct, list, and map. Historically, there are 2 types of Parquet readers in Spark. There is the non-vectorized reader and the vectorized reader. So the non-vectorized reader basically is just a fallback to the Parquet Java implementation, namely Parquet-MR. So it does support all the types, including like primitive types and the complex types. But because it operates on a row-by-row fashion, so the performance is really bad. So that's why it's a fallback implementation. On the other hand, we have the vectorized reader that was implemented from scratch in Spark. This only support primitive types until this feature comes in. Right? Primitive types contain like integer, float, timestamp, string, decimal, and so on and so forth. And it's quite fast because it scans data in batches. That is why it's called a vectorized reader. So we can take a deeper look on how those 2 types of readers operate underneath. First, the non-vectorized Parquet reader. As you can see, we still have the same data page as we showed earlier. On the right-hand side, you can see that essentially Spark operates on an iterator style. On the bottom of the chain, it's basically a scan operator that that just behave like an iterator, keep pulling data from the data source and return them as records to the computation. So in this case, the item type of the iterator is a single row. It's just a row, right? So in order to process the Parquet source, Spark basically just needs to, for each input, for each column in the read schema, it basically needs to first read the next repetition level, and the next definition level, and then the next value, right? And after it's done the process for all the columns in the read schema, it needs to assemble them into a single Spark record and then pass that to the computation. So as you can see that there's a lot of context switch here between the scan and the computation. The computation can be quite complex, and it could be filter, aggregation, sort, join, and so on. On the other hand, for the vectorized Parquet reader, it operates on batches. By default, a batch has 4,000 elements in it, right? So in this case, the scan is actually an iterator of record batches. So in terms of scan, Parquet Spark does no longer read one value at a time. Instead, it reads a batch of values at a time, right? So you can see that it reads a batch of repetition levels and followed by a batch of definition levels, and then followed by a batch of values. And then finally assemble that into a record batch and pass to the computation. So in summary, the advantages of the vectorized approach, first of all, because it operates on batches, that means that it tends to give much better memory locality and cache utilization, right? Because when you operate on batches, you have a higher chance to directly fetch from the CPU cache instead of having to load from memory. And also because it operates in batches, you can potentially apply certain optimizations such as Cindy in the read path. Secondly, in certain code passes, Spark can also use memory copy directly to copy data from Parquet into its columnar batch. This is true for instance, for integer type, because Parquet has the same in-memory representation of integer as Spark's in-memory representation in the columnar vector. So in that case, we can just directly copy the memory chunk instead of doing any processing. Lastly, Spark can also utilize certain encoding-specific optimizations to further speed up the scan performance. For instance, the repetition levels and definition levels, sometimes they are encoded using wrong-length encoding, right? Because, for instance, if you have 1,000 non-null values, in terms of definition levels, you can use wrong-length encoding, which just use 8 bytes of data to encode that information. And Spark is able to interleave the processing of those level information together with the processing of values that can further speed up the scan performance. So we have done some benchmark. Actually, this benchmark is already existing in Spark repo. As you can see on the right-hand side, for primitive types, we can get about 10 to 20 times improvement from the vectorized iterator. And the improvements are more significant for string types if you have a high cardinality of nodes. So this motivates us to really think about how to support complex type to get similar performance. So because of the time constraint, I cannot dive into too much detail about the implementation. But on a high level, there are 3 key things that Spark need to do in order to support complex type. First of all, as you know, that Spark, when it reads the Parquet file, it needs to convert the Parquet schema into Spark schema. During the process, you also need to check whether the two are actually consistent. So in this particular case, we need to augment the process by annotating the maximum repetition level and the definition level for each node in the Parquet schema, so that we can use the information later on to reassemble Parquet records. So we'll talk about a little bit about this in the next slide. The second thing that that Spark needs to do is to be able to read and materialize repetition levels, definition levels, and values. Previously, for primitive types, the logic is actually pretty simple. Spark does not need to really store the definition levels or repetition levels. It just needs to read them, because in that case, the definition level value is either 0 or 1. 0 means that the value is null, 1 means the value is not null. So you just need to read the value and process the actual values accordingly. But in the case of complex types, we need to actually store the repetition level, definition levels, and the values. So that adds more complexity to the logic. But we can do certain optimizations as well. So if we know that the repetition levels and definition levels, they are actually not needed, we can just skip them. So lastly, we need to assemble those 3 types of information into actual Spark records. So that's, we're starting from the leaf schema nodes. So Spark needs to utilize the maximum repetition and the definition level information gathered in the first step, and then reconstruct that into Spark records. So this is how a Parquet schema conversion looks like for a simple type. So here we have Parquet type that is a 2-level list, a list of integer, right? It's in Parquet, in Parquet format, basically it is represented on the right-left diagram. So to convert that into Spark schema, we first need to annotate the definition level and the repetition level for each node in the schema. Right? After we have that information, then we can pass that information into the Spark schema, and we have that in the bottom center slide diagram. So the complex type support is added in this Spark Jira, and with the feature right now, Spark can support all the types, all the complex types, including list, map, and struct. But we have a configuration to actually turn on or turn off the feature. In Spark 3.3, this is turned off by default because it's a new feature, so we don't want to run into risk. We want to gradually turn it on in the next few releases. So we did some benchmark with the feature. As you can see on the right-hand side, we get quite similar performance from reading struct fields comparing to the previous slide where we read primitive types, right? It's about 10 to 20 times improvements for those types. We also get about 3.5 improvements when reading array of structs or array of integers, array of primitive types, basically. Out of curiosity, we also did a benchmark using TP-CDS. Basically, for the TP-CDS benchmark, what we did is we didn't change the table schema, because in TP-CDS, the schema is just a flat schema, only contain primitive types. But we just basically enabled vectorization, enabled the vectorized reader and disabled the vectorized reader. We compare the two performance, right? We can see that with TP-CDS scale factor 1, and we can get about, in average, 2 times improvements. So because we can get similar performance when reading struct fields from the complex type support, we assume that if we change the TP-CDS schema to use complex types, like structs, we can also get similar performance. The next feature we'll talk about is Parquet index support. So this is another new feature that was shipped in Spark 3.2, which was released last year. So before we dive into the feature, we also need to talk about some of the background information, like how Parquet does predicate pushdown. Before the column index feature, Parquet has 3 filter mechanisms to push down predicates from Spark. The first one is called statistics. So this basically utilizes the column chunk statistics information to skip data. As mentioned earlier, each column chunk has its min and max statistics, right? So Spark can just basically pass the filter down to Parquet, so Parquet can compare the filter value against the min-max, and if it is out of the range, then basically Spark can just skip the entire row group. The second filter mechanism is called a dictionary. So this is very useful when the column chunk is encoded using dictionary encoding. That is when you only have a small number of unique values for the column chunk, right? In that case, there is a single dictionary page associated with each column chunk. So instead of applying the filter for all the data pages, Parquet can just apply the filter on the dictionary page. So that can dramatically improve the performance. For instance, if you have a dictionary of strings, basically Spark can pass down filters such as string start with, and then you can apply that filter on all the dictionary value instead of all the values in the pages. The last filter type is called the Bloom filter. And this is a new feature that's released in Parquet 1.12. So with this feature, basically, each column chunk can be associated with a Bloom filter. And then Spark can basically push down equality check predicates to the Bloom filter so that they can compare the predicate value with the Bloom filter and to efficiently do data skipping. So basically, all those 3 types of filter mechanisms, they only skip data on row group level. As you can see, that row group is usually pretty large. It has 128 megabyte by default, and sometimes even larger. So that is why column index is much more efficient in certain scenarios, because column index, unlike the previous filter mechanisms, it operates on page level. So it basically utilizes per page min-max information to be able to skip data pages efficiently. So because page in default has only one megabyte, so it's much, much smaller. So that means that with this filter mechanism, we can operate on a much finer granularity. So with the, basically, it's also most effective when data is sorted, right? Because with the column index, we utilize min-max information, and that information is most effective when you have the column chunk data sorted. It's also most effective when you have low selectivity. For instance, if you're only selecting a few rows across an entire column chunk, then you may just need to read a single page out of hundreds of pages. So in that way, you can save a lot of CPU and I/O. So this is another feature that was introduced in Parquet 1.11. So let's take a look at an example. In this case, we have a table with a single row group, assume that, and with two columns. Here we have C1 and C2, right? And we have C1, which is an integer type, and C2, which is a string type. And we have this query, which is pretty simple. You just select, all the rows from the table where C1 is greater than 3 and C2 is less than F, right? We have 5 pages for column C1 and 3 pages for column C2. You can see that to evaluate the filter C1 is greater than 3, essentially we need to select all the rows in the range from 4 to 9. In order to evaluate the filter C2 is less than F, we need to essentially select all the rows in the range from 0 to 4. Right? So all the rows that qualify for those two predicates is just a single one, which is row number 4. So with column index filtering, we can essentially filter out all the other pages except 2 in this particular case. Well, with other filter mechanisms like statistics, we still have to read the entire row group. And in particular, for this particular case, inside data page 3 of C1 and data page 2 of C2, we only need to read one row, right? For instance, in data page number 3 of C1, we only need to read the first value, but we need to remember to skip the second value. And similarly for data page number 2 of C2. So in order to do that, there are two key concepts that are in the column index filter implementation. That is the first row index and the row range. So the first row index is basically the first row, the first row of a page, right? Because row is sequentially ordered, so you need to remember what is the first row for each page in order to skip records within a page. And the row range is basically a range of rows that you need to select after applying the column index filter. So in this particular example, you can see for the first row group, we have first row index equal to 0, 2, 4, 6, and 8. And for the column C2, the first row index is 0, 3, and 6, that matching the number of values in each page. And the row range in this example is pretty simple. It's just 4, because after the filtering, we only have one row selected, so the row range is just single one. But in practice, you could have many row ranges. So to support columnar index in Spark, on a high level, we need to do a few things as well. So because of the time constraint, I cannot jump into the details, but this is how we are doing it on a high level. First of all, Parquet, after the filter, it passes Spark several information, right? It tells you the first row index for each page after the skipping. It also tells Spark the row ranges for all the selected records. So Spark basically needs to process those two information and remember within a data page what records need to be skipped. You also need to add new logic in order to skip values because even within a single page, you still need to skip values based on the row range. And so basically for plain encoding, if the value is encoded using like a native plain encoding, then Spark can simply just skip the value, skip the data from the input stream. Lastly, to process row range in the vector accelerator, basically Spark has two ranges to compare to. The vector accelerator basically operates on batches of rows. So you have a batch of records starting from position, ending a position. And you also have row ranges passed by Parquet. So Spark basically needs to compare those two ranges and perform certain operations depending on its relationship. If the row range is before the current record batch, then basically Spark needs to completely skip this current row range and then advance to the next row range from Parquet. And if the row range is after the current batch, then basically Spark can just completely skip the current batch of data because they're not selected. And also if the row range is overlap with the current batch, then you need to basically do some more complex operation like selecting those records that they overlap and skip the rest of the records. So this is the performance we get from the columnar index. So you can see that this is basically a simple benchmark. We have about 15 million of rows stored in a single column chunk. And so if we just select a single row from this data, we can get about 10 to 26 times improvements, depending on the data type. There are also more benchmark results in another blog post published by Cloudera some time back that has more complete benchmark results. I suggest you to check out there as well. So with that, I'll also talk about some of the future work we can do to further improve Parquet performance. So there are mainly two features we can work on in future. First one is called decoding I/O on the CPU during Parquet scan. As you may know that currently, many Parquet files are stored in cloud storage like S3, right? And the I/O cost is pretty expensive there. At the moment, Spark process Parquet row groups actually in a sequential fashion. So basically, in order to read a single row group, Spark needs to first download the row group from HDFS, S3, or other cloud provider, and then it starts to process the data, basically decompress and decoding, right? So this you can see is quite inefficient because when you are downloading the data, the CPU just sit idle and wasted. So there's actually some in-progress work on this feature, which is basically described in these two JIRAs, Parquet and Hadoop, respectively. In Parquet, this work is ongoing, and there's actually a nice API introduced in Hadoop, in the upcoming Hadoop release, which allows you to read a set of ranges within a single file in parallel. So that means that you can download the data in a much more efficient way. The second feature is called lazy materialization. So this is basically this means that when reading Parquet data, we evaluate the filter first and then materialize the data. So in the current implementation, basically, Spark will, if you are reading, say, 100 columns of data, well, you have a very selective predicate on a single column, then Spark still needs to read the whole 100 columns of data and then apply the filter. And potentially, like 99% of the data are filtered out, but you still need to read them. So this is kind of expensive. So on the other hand, the latency materialization basically swap the order. You first apply the filter dynamically, and then you download the data. So this can potentially help a lot to improve scan efficiency. So the idea is actually similar to column index in that you can skip data pages, but unlike column index, where you can only push down certain predicates to Parquet, comparing with the min-max information, right? But here, with latency materialization, you can actually have more complex filters, such as UDF, other things. You can evaluate those dynamically and skip the data efficiently. This also is more useful if you have older Parquet files that's written without the column index feature. The column index was released in Parquet 1.11, which was relatively recently. So with that, that's all my slides. Thank you so much.